Hello, welcome to lecture 10, part B. That's the last part of Bender's decomposition in this course. I planned to teach it yesterday, but because of the time restrictions, I had to have it in today's lecture. So here we are going to talk about nested Bender's decomposition applicable to multi-stage stochastic programming problems. Good. Let's see what nested Bender's decomposition is. Well, hopefully after this session, you will be able to explain how nested Bender's decomposition works and hopefully implement it to a stylized problem. Well, yesterday we had a long discussion about two-stage stochastic program and its applications to power systems and power and energy systems. So in general, in two-stage stochastic programs, we have first stage and second stage with here and now decisions and wait and see decisions. So for example, I mean, we talked about a few examples of or applications of two-stage stochastic program in power and energy systems. You can list many applications, but just I mean, a few examples are, for example, the two settlement market clearing, stochastic market clearing, assuming or taking into account day ahead and real time or balancing stages, right? While here, the potential source of uncertainty could be wind power production to be realized in the second stage, or load level to be realized in the second stage, or even contingencies, any failure of assets, either generation assets or transmission assets or any other assets. But how to generate scenarios? Well, I already shared with you a lot of, references about how to generate scenarios. Assuming correlations. But whatever we do, we generate scenarios in the day ahead stage based on our available information in that stage, because we are solving this problem in the first stage. So we should generate our scenarios based on the information we have in the first stage. So for example, in the two-stage stochastic market clearing problem, the day-ahead decisions could be production dispatch of generators, either conventional generators or renewables, or if we solve unit commitment problem, then also the commitment of conventional generators, they are also first stage variables. And the balancing decisions are the redispatch of generators, or how much reserve we have to call to be activated, or load shedding and wind spillage as extreme costly recourse actions in the second stage. Other applications could be, we also talked about the optimal contract decisions of a price taker producer. Also, you can call it a self-scheduling problem, where a price taker producer decides in a bilateral stage. It could be week ahead, it could be months ahead, it could be year ahead. The price taker producer decides how much what the optimal bilateral contract decisions is, and then our scenarios in this case are, let's say, market prices. So the market price or load level, if it's relevant, it's the potential source of uncertainty. The first stage decisions, we are generate scenarios in the first stage, in the contracting stage, and our optimal decisions, or variables in the first stage is optimal contracts to be signed to bilateral contracts, and the second stage decisions are production quantities to be sold in the market. So yesterday, in the previous lecture, we formulate a two-stage stochastic program in a generic form. I call it form 1. And there we have two types of variables: first stage variables without index scenario omega, and the second stage variables with index omega. Then first stage cost, expected second stage cost. So phi omega is probability assigned for scenario omega, and g of omega y is our let's say recourse cost in the second stage corresponding to scenario omega. Then we can think of first stage constraint and linking constraint that links the first stage variable and second stage variables. That's the simplest compact formulation of the two-stage problem. Yeah, so as I said, x is the fixed first stage variable, y omega is the second stage variables. They are scenario dependent. The word scenario independent might be a bit misleading. By scenario independent, it means that it's not indexed by omega. But of course, scenarios, they are impacting the optimal value of x. So one may find this word is a bit misleading. And phi omega is the probability of scenario omega. So is this problem decomposable? Yesterday we saw yes, x is our complicating variable. So if we fix it, then we will have one subproblem per scenario. So this is the first form of formulation of two-stage stochastic program. Also, I think we also talked before, we can write it equivalently in a different way, but it's equivalent. I call it form 2. Here, this time, let me change the color. X, the first stage variable, is also scenario dependent. So everywhere X has index omega, but then we have additional constraint saying that for all scenarios, so omega and omega tilde, they are the same set of scenarios. So for all scenarios, the decision, our optimal decision for first stage variable x omega should be the same. It's equivalent, right? Do you agree? Maybe in the chat box? Yes. A lot of yes I got in the chat box, not a lot. I got 3, but it's increasing. And yesterday, not yesterday, last time we saw that its typical name is non-anticipativity conditions. Why we call it? Because it prevents anticipating future information. If we don't have it, the first stage variable will take different values for different scenarios. But since we don't know which scenario will be realized in the day ahead, so this condition, this constraint prevents us to anticipate what the optimal value for the first stage is depending to each scenario. So this is why we call it non-anticipativity condition. Good. And is this problem decomposable? We already talked about that, and the answer is yes. This constraint is complicating constraint, meaning that if we relax it, then the original problem can be decomposed per scenario, right? Yesterday we had a figure like, we had a Caesar cutting the scenario tree, and here is exactly the same. Also, if we relax non-anticipativity condition, we are disconnecting scenarios together. It means that we have one subproblem per scenario, but over iterations in a decomposition techniques, we have to restore this condition. How? We will talk about it today and tomorrow. But the main point of this lecture is if we go beyond two-stage programs, if we have 3-stage, 4-stage, or in general, multi-stage stochastic program. So let's start with the simplest version, three-stage. We will generalize it to multi-stage later. But we have here first stage, second stage, and third stage. I think a few of you are doing your projects kind of 3-stage, so maybe it's interesting to you. Sorry. So a few examples, if we generalize or extend our previous examples. So in 2-stage example, we had day ahead and balancing stage. Now, in the middle, we have an additional stage, it's intraday. So what happens here? So again, we are solving our problem in the day ahead stage. So we generate our scenarios to be realized in intraday stage and real-time stage. We generate those scenarios based on our information in the day ahead stage, right? But there are some dependencies. How? For example, we say that under this scenario, the intraday price, it might be $10, $10 per megawatt hour. So it's our first scenario for the intraday market price. And then we say that if intraday market price is 10, then the two corresponding scenarios for the balancing stage price is either 11 or 9. So our scenario 3 says that the balancing real-time prices as uncertain parameters is either 11 or 9, providing that the intraday price to be realized earlier was 10. Or for example, here we say that the intraday price is 15, and if intraday price is 15, we anticipate, or it's our scenarios that the two real-time prices, balancing prices, will be either, I don't know, 14 or 16, right? So we don't have a scenario saying that the balancing price is 14 while the intraday price is 10. It's not in our scenarios. Is it clear? Yes? Good. So so hopefully you got what this three-stage stochastic tree says. Good. So this was one example for three-stage problem application in power systems. Yes, it was one example. This is the formulation, the generic formulation of three-stage problem. Could you please check it out for a minute and try to interpret what each constraint means and what is the objective function? Maybe after 1 minute, one of you can unmute and explain your thoughts. Okay, any volunteer try to interpret what this formulation says?
I can try.
Yes, yes, Amos.
So I think you're minimizing the expected cost over your scenario set omega, where phi omega is the scenario probability. And then there are cost functions for the three stages, which are f for the first stage, g for the second stage, and h for the third stage. Then there are constraints for the referring to the first stage, which is the first constraint. And then there are constraints referring to linking all three stages, which is the second constraint. And then there are non-anticipativity constraints for the first and second stage.
Okay, very good. Amos, we have omega, while in the previous slide, I said we have two sources of, let's say, uncertainties, intraday and real time. But here we have only one index for scenarios, which is omega. This omega refers to our scenarios in the second stage or in the third stage.
Well, I think you formulated it here in a way that it refers to both. So you can, for example, if you have two, sort of your scenario tree here splits into two decision nodes in the second stage and into two more in the third stage, then you can say that for scenario one, the non-anticipativity in the second stage bundles the second stage decisions for scenario 1 and 2.
Okay, let's try. Let me say I have here, I have 4 scenarios in the last stage. So W omega 1, omega 2, omega 3, omega 4. Okay. Let's see what they are. And what omega 1 is, omega 1 says that if this happens under omega 1, here the intraday price is 10, the balancing price is, I don't know, 15, for example. So omega 1 includes, let's say, 2 dots. It's 10 and 15, 10 for intraday and 15 for real time, right? So this is the definition of omega 1. Good. Now, omega 1 includes all the uncertainties to be realized in the past from the node to the specific, let's say, leaf. So this is my definition for omega 1. Is it clear? Then let's start with this non-anticipativity. What does it say? Amos, if you like to say, continue.
It means that all first stage decisions need to be equal across scenarios.
Yes, it says that though we have 4 scenarios, so omega is from omega 1 to omega 4, and the same for omega prime. It's omega 1, omega 2, omega 3, and omega 4. Good. So it says that for all scenarios, whatever happens, our decision in the first stage is unique. It takes only one value. Okay, the tricky one, Amos, is the last one. What does it say? What do you think theta? This is theta, right? Maybe.
Yes.
Maybe I'm wrong. Okay.
I think what this means is that the second stage decisions for scenarios 1 and 2 need to be equal, as well as the second stage decisions for scenario 3 and 4. And I guess this theta is some indicator showing if the scenarios are bundled in the second stage in that sense.
Let's understand better. So you're saying that this constraint for this application says that our decision for stage 2 for scenario 1 is equal to the same decision in the second stage for scenario 2, and the same for scenario 3. This is S2 and scenario 4, right? And I agree. This constraint for this application that we have, it includes 2 conditions, because here our decision, second stage decision for scenarios 1 and 2, and also for scenarios 3 and 4, they are identical. So any better description what these thetas are? Look at here, maybe.
I'm trying to how you
they are our uncertain parameters, right? So they say that if in stage 2 or until stage 2 our uncertain parameters are the same, so here our uncertain parameters for stage 2 is 10, right? It says that, okay, also for omega 2, if I write it's 10 but not 15, let's say 17. It says that for omega 1 and omega 2, our corresponding uncertain parameters in that stage both is 10. So this means that theta, their thetas are equal. So thetas are uncertain parameters related to that stage, and therefore their corresponding decisions in that stage should be identical. So yes, thetas, they are uncertain variables related to corresponding stage. Is it clear to everyone? Can you write in the chat box that it was clear? Okay. So we got agreed what these thetas are. So they say that as long as for stage 2, the corresponding uncertain parameters to be revealed in stage 2, they are identical, like this point for scenarios 1 and 2, then their corresponding decisions in that stage should also be the same, right? So as I said, again, let's go for this example just to make sure. So for scenario 1, we say theta 1, theta of scenario 1. Oh, let me say something this way. So for scenario 1, the uncertain parameter in stage 2 is $10. It's the intraday market price. While for scenario 1, our uncertain parameter to be realized, it's 11. So for scenario 2, our scenario 2, so it's 2. In stage 2, the intraday market price uncertainty to be realized is 10. So this is real time. And for the same scenario, the corresponding real-time price this time is, let's say, 12, right? Is it clear? And the same for scenarios 3 and 4. So now you are saying that for scenarios 1 and 2, in stage 2, their corresponding uncertain parameter is equal, so their corresponding decision in the second stage should be equal. Yeah, uncertain variables, they are, uncertain parameters. Okay, I call it uncertain parameters, random variables. Sometimes I'm saying random variables equivalent as uncertain parameters. So I correct what I said. So thetas are, random variables, or if you like, you can call it uncertain parameters. Clear? Uncertain parameters in the second stage. Good. This is uncertain parameters in the second stage, uncertain parameters in the third stage under scenario 1. Good. Let's continue. Yeah, so this is uncertain parameters, 2 non-anticipatory conditions. And thanks to Amos, this is our probability for each scenario. Objective functions, constraint for the first stage, the linking constraints. Good. Multi-stage stochastic problems. So now we have, for example could be generation expansion planning problems in different years. Peter, yes, please.
So this is this is all defined when the scenario is made as a tree.
Yes.
And it has to be like that.
Yeah, if you don't go for a tree, then you may have numerous number of scenarios, right? And also it makes sense, for example, if you put conditions for your scenarios in second and third stage. So you are kind of putting or generating conditional scenarios. You're saying that the real-time price will be, this if already the real-time price was that. I think it's a more elegant way to generate scenarios for 3-stage problem. Or you don't agree?
Well, I come from a different background. Okay. Let me just put it like that. The thing is that I'm not doing it this way. I'm using I'm simulating in another way. And the results don't really make sense. And I think it is because if you don't have these nodes in the different stages from which you then move on to, then you don't have this non-anticipativity as a natural thing. And then, yeah, never mind that.
Okay.
You think it's more beautiful in scenario 3 version. I
think
buy
it's
into that.
more realistic, more elegant. That's my feeling, my impression. But yeah, you may say you disagree, but that's my impression. Maybe we can argue about it later.
Yeah, let's do that.
Yes, definitely. I'll be happy to do that. Okay, so this is the multi-stage stochastic program, not necessarily 3. Okay, now I ask you to interpret this formulation. Please check it out for 30 seconds, and maybe one of you can unmute. Anyone who would like to explain what this formulation is? Yeah, specifically the last constraint. What T is, what T tilde is, what omega and omega tilde are. Yeah, Drake, please.
So just the extension of the formula that was on the last slide, where in this case, the T tilde is all of the, for any stage T tilde is the set of, or rather, for every T tilde that is less than T, it's all of the stages that have previously been fixed by that stage's optimization. So in stage 3, we would need both the T2 and T1 X's to be set if, or to be equal to that, the optimal X at the previous stage if the uncertainty parameters for that stage all match. Effectively, it's saying is for one branch of the tree, all of the decisions at the subsequent node must depend on the whole branch history.
Very good, very good. Drake, I totally agree. Just to go, I mean, in a slower pace. So T is index of stages. T tilde is index of previous and current stages, right? And current stages. What does it mean? It means that, for example, if we are in stage 3, then T tilde is stages 1, stages 2, and stages 3, right? What omega is it the scenarios to be counted in the first stage, second stage, or the last stage? Let's say here I have 5 nodes, here I have 2 nodes, here I have 1,000 nodes. How many omegas do we have? Last stage, exactly. So here's omega 1, omega 2, blah, 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 omega, let's say 100 or 1,000. Good. So as Drake said, well, objective function, I think it's clear. This is the constraint, linking constraint, or whatever kind of constraint you have. The critical constraint is the last one, non-anticipativity conditions. So it says that in stage T, we have non-anticipativity, or if the uncertain parameters from stage 1 till that stage, they have exactly the same uncertain parameters. Then the corresponding decisions in that stage should be equal. For example, let me change the color. For example, we are here. It says that here in these 2 stages, their corresponding uncertainty parameters in the history of these 2 nodes, they are equal. Oh, sorry, I did wrong. I said wrong. Sorry. So let's say for this, yeah. Okay. If we are in this node, and then we have omega 1 and omega 2, it says that until stage 3, all the uncertain parameters to be realized for scenario 1 and scenario 2, they are equal. So our decision for scenario 1 and scenario 2 in stage 3 should be identical. Clear? Ianis asked, so in this formulation, Do we assign decision variables to the nodes in the scenario tree, or we introduce decision variables for each decision state of each scenario? So for example, it's, let's say, so in the previous stage, I had superscript S1, S2, S3. Now I got rid of superscript. I bring it as an index to subscript. So it's, for example, X in stage 1 under scenario 1, or X in stage 1 under scenario 2. That's a different type of definition. Brian said in slide 10, what is the difference if we run two-stage problems for the generation expansion every few years using a rolling window criterion? I'm not talking about the rolling window for now, Brian. Let's focus on single problem. We are solving it before the first stage. Just let's to understand what this formulation is. Is there any question? When we solve this problem, we solve this problem here in the first stage. Is it clear? If you're right, it's clear in the chat box. I can move on. Yeah, only 5 clear I got in the chat box. For others, is it clear? Okay, good. So T is index for stages, non-anticipativity conditions, and uncertainty parameters related to scenario and stages. Well, now we reached the interesting point. So far, just it was the formulation of multi-stage stochastic program. How to use benders to solve it. To solve a multi-stage stochastic program, you have different options. Solve it directly, but good luck. Okay. The second one is affine policy or linear decision rule. I'm not going to talk about that. It's an approximation approach. And there you assume that there is a linear dependency between decision variables and uncertainty parameters. This assumption will help you a lot to approximate and shrink your problem. But I'm not going to teach it, but if you like, I can provide some references, but also you can easily search for affine policy or linear decision rules for multi-stage stochastic problems. You will get a lot of very good papers. There are very nice papers by in the group of Daniel Kuhn, Professor Daniel Kuhn from EPFL, you can find. The other approach is Lagrangian relaxation that we will talk later, not in this lecture, but yeah, we will talk in the rest of the course. So I skip it for now, but the whole idea is to relax the complicating constraint, which is in our case non-anticipativity constraints. But also there is one alternative, nested benders, which is based on fixing complicating variables. But how does it work? This is exactly what I'm going to say in the next slides. Also, Brian said dynamic programming. Yeah, that's also true. Okay, I have to add dynamic programming. Yeah, I missed it. Thank you so much, Brian, for mentioning. Good. So maybe I can add etc. here. So just not to say that this is the only approaches. Very good catch, Brian. So let's talk about nested benders. I learned a lot from this archive paper from James Murphy from Cambridge. So this is also the figure from that paper. Let's go for the four-stage problem, but you can extend it to, I don't know, any stage stochastic program. I was relieving the answer of the questions I'm gonna ask. We would like to use benders. Already you saw how to implement benders to two-stage stochastic program. Here, but we have four-stage. any idea how to use benders to this 4-stage problem? Any clue?
You can look at the whole tree as a set of nested 2-stage stochastic problems.
Yeah, good. What do you mean by nested?
Like if you see like the root node, and then you see the second stage, all the different nodes. This is one 2-stage stochastic problem, right? And
Yes.
then you go to a second stage, you have 3 nodes, and then you can look at the first of these 3 nodes and the other nodes, and this is another 2-stage stochastic problem. So at the end, you're going to have several 2-stage stochastic problems which are going to be nested.
Exactly. Thank you so much, Brian. It was exactly correct. So if you check it, this is 2-stage problem in the first and second. That's one. We are gonna try to find as many as 2-stage problems we can find in this 4-stage problem. So then here we have 3 more 2-stage problems. Then here we have again many 2-stage problems in the last 2 stages. And these 2 stages, they are located together in a nested way. This is why we are going to call it nested benders. Is it clear? Very good. Yeah, Drake said it's clear. Yeah, Drake, I know also in Imperial College, yeah, our colleagues, they work very nicely on this type of problems and their applications to power and energy systems. Also, our colleagues in Brazil, mostly for hydrothermal scheduling applications, they did very interesting works for nested benders. Anyway, but as I explained, we have 1 2-stage here, 3 2-stage here, many 2 stages in the last many 2-stage stochastic programs at the end. So this is, if you check it out, a multi-stage problem is a nested series of 2-stage problems. And this is why we are going to use benders in a nested way. We will call it nested benders. Also, if you remember, we called also benders as dual dynamic programming. So this technique also is stochastic dual dynamic programming, in abbreviation SDDP. Also it's very similar to nested benders. Just in my knowledge that in STDP compared to nested, I'll explain. You don't need to go for all nested benders. You can do some sampling in later stages. But if you see some, I don't know, STDP, stochastic dual dynamic programming, it's a very similar approach to nested benders. Though if you have many 2 stages, maybe at some point start to picking or clustering the last 2 stages and not to solve all 2-stage stochastic programmings in the later stages by sampling, by clustering, whatever. Is it clear what I'm saying? Hopefully it is. Okay, recall in the 2-stage problem, the first stage variables, they are complicating variables. So similar to benders, in nested benders, it's an iterative approach. In each iteration, we need to solve not one problem, but several 2-stage stochastic programs. Let's see how it is. Again, it's an example I took from the paper from James Murphy I mentioned. So let's go for this. We have 3-stage problem, 1 node in the first stage, 3 nodes in second stage, and 6 nodes in the third stage. Just an example. Okay, let's see how we can implement nested benders. Also, you will help me. Let's say we are in iteration 1, but also in each iteration, we have a few steps. We are now iteration 1, step 1. And the mission is to solve the problem, the optimization problem corresponding to node A in the first stage. So we learned the nested benders, we go first for the first two-stage problem. So you can tell me A for BCD, is it a master problem or subproblem? Remember, in the two-stage problem, we fix the first stage and we update it in the master problem. So here A, for solving A, do I need to write master problem or subproblem? Brian says master. What about the others? Let me explain again. In the two-stage problem, if you remember, we had X and we had Y omega. We fixed X, so it was master problem who was updating X. And then for given X, we solve Y omega in subproblems, one per scenario. Is it clear? So now our decision in the first stage is XA. XA. It means that X in node A. So to be able to solve, I mean, you agree that we are going to start with the master problem because A is the first stage variable. It's the complicating variable for stages B, C, for nodes B, C, and D. Is it clear? Yes. Good. So let's see, what does it mean? It means X, it's our vector for node A in step 1. Okay, so we are in iteration 1. Sorry, not step 1. I corrected, in iteration 1. So X is our nodal variable in node A in iteration 1. Good. So this optimization problem is just a master problem. So we need to have auxiliary variable alpha, again with superscript A1, means that it's for node A iteration 1. And let's say a local constraint. And upper bound for alpha, since we are starting here first with the master problem. What does alpha A1 represent? Do you remember? What does alpha A1 represent? The whole future cost, right? The old future cost. The future cost when we are in node A. Nice. So I hope it's clear so far. Now in a forward direction, we move forward. Now we are gonna write 3 two-stage problems. One in B, one in C, one in node D. For example, just let's go for the first one, but you can do the same for the other two-stage problems. Now you have to tell me, node B. For node B, do we need to write a master problem or a subproblem? Or we can say like this, B. Is it, do we have a complicating variable there or not? The corresponding optimization problem for B, is it a master problem or is it a subproblem? Goran says master. Drake, Hosna, Carolina, Eric, they are saying both. Exactly. B is a subproblem for A, but master problem for A and F. So we are gonna write a mix of master and subproblem for B, right? So what happens? Again, XB1 means the variable in node B still in iteration 1, okay? Since it's a master problem, so we have the local objective function plus alpha B1 What does alpha B1 represent? The future cost coming from nodes E and F, right? But since it's a subproblem at the same time, so we have a local constraint as a function of first stage variable xa1, whose value is fixed, coming from the same iteration previous step. And by this dual variable, I mean that it's a dual variable that we fix the value of the variable of node A in iteration 1 within the problem of node B in iteration 1. So is it clear that this is a kind of a mixture of master and subproblem? Clear? Very good. We move forward. Step 3, iteration 1, still iteration 1. Now we have to write six optimization problems, 1 per node. But let's pick E as an example, but you need to write similar things for F, G, H, I, G, J. So node E, is it master problem, subproblem, or a mixture? Carolina says subproblem, Hosna subproblem, and I agree. I hope everyone says, yeah, subproblem only. So no alpha, just the local optimization problem. And E1 means the variable of node E in iteration 1. So since it's just subproblem, there's nothing related to master problem. So we need to fix the value coming from the previous node B in the same iteration 1 and the fixing constraint and its corresponding dual variable. Is it clear? Do you have any question here, a tricky question here? Did I take an assumption in this formulation? Any simplifying assumption? Let's say this is a day-ahead problem, day-ahead stage, intraday, and real time. And then I say the value, the intraday variable is fixed in the balancing stage. Fine. Okay, the assumption I take is that I assume that the first stage variable didn't appear in node E. This is the assumption I took. Is it clear? If you write yes, I'll be very happy in the chat box. So this is the assumption, simplifying assumption I took. This assumption will be relaxed later as an exercise. So I'll ask you to think how to extend this formulation, what to do if our problem in E is dependent not only on B, also but on A, the variables of B and A. Carolina said, I didn't understand. Okay, what about if here I have another term, let's say, I don't know, G of XA1. So our now problem in E, it depends not only on the variable of the previous stage, but also the the stage 1. If I do that, maybe I need to write another fixing constraint. Maybe. So this is what I like to ask you to think about. Is it clear, Carolina, now? Carolina? Yes, very good. Okay, what should we do next? Any guess? Yeah, Brian says another assumption is that you always have feasible problem. Yes, always. Yeah. Yes, I like two-stage problem. I assume I always have feasible problem. If I don't have, I can add the slack variables. That's an assumption I took from the beginning of Bender's decomposition lecture. But very well mentioned, Brian. Okay, now we are here. We in the forward direction, we reached the last node. What should we do now? Any clue? What's the next step? Backward. Very good. Now it's the time to get back to the first node. Now I count iteration 2. Some literatures, they keep it still iteration 1. It's more convenient for me to say now we are in iteration 2. Up to you how you like to define. Now, okay, again, we have 3 nodes, B, C, and D. Let's go for B. We already saw that B is a subproblem for A, master problem for E and F. So we have a mixture of problems. But now, do we have some new information that we can use? What is changed? Do we have something to use in iteration 2? Yes, Drake says we have E and F's solutions. So it means that what can we add? Yes, Kelly says we have dual variables. I agree. So now what we can do in B? What should I add? I should add Bender's cuts. Exactly. Thank you. So now my variable is B2, stage B, sorry, node B in iteration 2. Okay. Again, alpha B2 means the future cost for node B, which are E and F. So first, let's check this constraint. Here now I have B2, but here I have A1. Is it the typo or is it correct? Shall I write A2 or A1? Drake says A1. Why, Drake?
Because we haven't gotten that far back up the tree yet. We haven't done A2 yet.
Yes, very good. The most updated information I have from node A comes from iteration 1. So the most updated information is still A1. So I have to keep it A1. Yeah, the lower bound, we are, yeah, you see, still it's A1. Bender's cuts. In the compact form, you remember it's the objective function of the subproblems in the previous iteration. They are given, plus the sensitivities in the previous iteration. They are given. They are, yeah, from iteration 1. This is tricky. So it's our local variable in node B, variable iteration, current iteration 2, and the previous iteration 1. John asked, Jalal, did you change the slides? There are some color differences with the slides I downloaded. Yeah, I made it red just a few minutes ago, but yeah, nothing more change. Good catch, John. Good. Now node A. What shall I do? Should I add something to node A optimization problem? The same, right? Cuts, and A is just a master problem. So in the same way, now we have variable A2, alpha A2. Alpha represents the future cost for node A. So what does it mean? Can you help me, this cut? Can you help me to interpret it? This is the variable. What is this? Could you please help me? What is this term? this term. Objective function at B. Exactly, objective function at B. And note that we have to account the future cost related to node B. This is for node C, this is for node D. And for all of them, we have 2 because we got updated information. Yeah, this is nice, right? This is sensitivities when A1 was fixed in B iteration 2. The most updated sensitivities we got. And the nodal variable in the current iteration and previous iteration. Is it clear? Yes. Convergence criteria. We know that in two-stage stochastic programming, the value of alpha in the master problem should converge to the value of objective function of subproblems, all of them. In the iteration, we got converged. So what about here? We have 1 alpha per node. Do we need to get this convergence for all nodes or not? Direct says for all nodes. Yannick says BCD. Remember here, alpha of the first node kinda includes the alpha of the second stage. So I think alpha of the first node is enough because it already represents B, C, and D. This is my impression. I think it's enough, but maybe you disagree and we can argue. Yep.
Jalal,
Yes.
in Murphy papers, he mentioned that to terminate a problem, we require that all the subproblems have reached an optimal solution.
Okay. It was my impression that 1 is enough, but yeah, I agree that what you are saying is more restricting, but I don't see right away a reason if alpha of A2 is converged. I mean, we get convergence in node A. Why not we got convergence in B, C, and D? Why should it happen? Is my question clear?
I mean, I try a 3-stage stochastic problem, and I tried like the way you're mentioning. I mean, I haven't finished that project yet, but I saw like there was something weird with my upper bound and lower bound. So, and then I maybe said like I need to check that all subproblems have reached an optimal solution. So
okay.
I'm still working on that.
Well, okay. I'm not saying this term very, with a certainty. My first impression is that it's enough, but Brian maybe has more experience and saying that no, we have to check for all nodes. Anyway, I'll leave it as an open question.
Okay, thanks.
Exercise, I already revealed. If we go for a bit complicated setup, it means that variable of node A appears not only in the second stage, but also in the third stage. What kind of alternatives do we have? So maybe you would like to think of and share your thoughts in exercise session tomorrow or on Monday. Good, that's it. I know the time is over, but was it clear or do you have any question? Is it something exciting or not? It looks complicated to you. Maybe you can write your impression. No, Brian, I didn't try. Prabhat says a little complicated. But was it clear? Did you get the concept? Prabhat says yes. John says, I think it's useful to know the extension for multi-stage problems. Yes, I believe so. Direct says, is the first forward pass only run once to get initial values? I'm trying to understand your question. The forward pass, No, we solve first the A, right? And in A, we derive the optimal value for X in A. So we start with master problem. So I don't think we need initial guess. That's my impression, Drake. I don't know if I answered your question or not. Nuran says concept is clear, requires some experience. Definitely. Peter says clear, exciting, but have to get my head around a thing or two. Good. Ingrid says quite complicated, but I got the concept and general idea. Nice. Daniel says the concept is clear. How to actually implement it into a real problem, that's a different story. I fully agree with you, Daniel. Hosna says clear and interesting, but seems complicated in practice. Yeah. Yes. So if you're interested, also check the literature about SDDP, stochastic dual dynamic programming. As I said, if we go for 10-stage problems with millions of scenarios in the last stage, how many 2-stage problems you have to solve? Oh my God. So some people, they do some clustering and sampling things to, how to say, approximate the sensitivity. That's one thing. Also, I saw some papers from our colleagues that if we have binaries in the forward stage that we don't need cuts, sensitivities, they, am I right? No, I said wrong. In the forward stage that we need to derive sensitivities, they relax binaries, while in the backward stage, when we generate cuts, but we don't need to derive sensitivities, I guess, if I'm not wrong, they put binaries as they are. There are some tricks like that, but it's heuristics. Nicholas said, do you keep moving back and forth then until you have convergence? Yes, definitely, Nicholas. So in my definition, iteration 1 is forward, 2 backward, 3 forward, 4 backward. Okay, we are out of the time. Now it's 5:12. I suggest we go for 30 minutes break. So we'll start at 25 past 5. Yannick asked, but we drive the duals in backward. Maybe I said wrong. The answer, general answer is that whenever we don't need to drive duals, we can relax binaries. I didn't read the paper in depth, but the whole idea is that when just we add cuts, yeah, that's what I said. Whenever you don't need to get sensitivities in those iterations or steps, you can relax it. Anyway, it's heuristic at the end of the day. 25 past 5, we can start a new lecture about Lagrangian relaxation. See you in 12 minutes.